So, hi everyone, I'm Abir. I just finished my master's degree. The project I will be presenting now, it was my master's thesis, and I worked on it with Florent and Gigine. Um, yeah, and I will be at MNOP, so looking forward to meeting you all. Florent?
Okay, so hi everyone. It's the first time I meet the group, it seems. So I'm a PhD at the Max Planck in Germany with Bernhard Schulkopf, so where teaching is once every 3 weeks, let's say. And yeah, I worked together with Abir on this project, more on the method side for mechanistic interpretability, but I'm happy to talk more generally with all of you at different times. So yeah. Good luck, Abir.
Yeah, thank you. Yeah, so as I said, I will briefly talk about our paper that we submitted to AR, tracing multilingual representations in LLMs with cross-layer transcoders. So as we all know, there is this multilingual performance gap that Gopal mentioned too. Basically, it was spot before, but yeah, it's also present in LLMs, and as we know, many people don't have English as their primary language, so this induces linguistic bias and economic implications for those people. There has been some work to analyze and interpret language processing in LLMs. One of these work was by Wendler, and they basically used LogicLens to on a bunch of tasks like those that I presented here to finally show that multilingual models process non-English inputs by routing through English representations in intermediate layers. So just like as we see here, the model was asked to translate flower from French to Chinese, and there has been some traces of flower in the middle layer before it predicts flower in Chinese. The same thing was done by in this work, the multilingual LLMs think in English, but on an open-ended generation task. The same results were achieved, but with this slight tweak that they also show that um, articles or determinants don't have this switch into English. But as we see, the work was limited in the tools used, and hence our project. So in this presentation, I will go briefly through like the mechanistic interpretability tools that we can use to interpret LLMs. And then I will try to answer some questions like, do LLMs really think in English? Why do models fail in non-English languages? How do models handle language? And I will end with some conclusions. So how do we interpret LLMs? I have a bunch of slides here talking about like the linearity hypothesis on which mechanistic interpretability tools are built, which is basically that concepts are represented as directions in high-dimensional space, and semantic relationships can be represented as linear transformations. With this very known example of king minus man plus woman can give you queen. But when we look inside models, there is this puzzle that neurons aren't clean and interpretable because basically models only have millions or billions of parameters, but way more concepts to represent. And this has been shown in this work of toy models of superposition in 2022, where they show basically that neurons are polysemantic and they represent many concepts at the same time. The question is, how do we disentangle these representations? So one tool that has been introduced in this work of 2023 is to use something called sparse autoencoders to recover those sparse features or sparse directions, which was basically just taking the activations of the model in like in a point inside the model. It can be an MLP or attention or anything. Apply on it an encoder decoder to get a larger vector that represents your features. Um, this is basically just projecting on an overcomplete basis, and you get your features that are uh, reconstructing what your actual activations did, but at the same time, they are sparse. And so you can recover some sparse representations, and you can end up having features, or you can end up disentangling your representations and getting features that actually make sense and are somehow interpretable. And some of the examples that were like presenting this concept of features and how this method can be useful is this Golden Gate Bridge from the same 2023 Anthropic post, where they found that they showed that there is a feature that activates on Golden Gate Bridge in text, but also in images. But the problem with SAEs is that they really don't trace the dynamics across layers. And this is where cross-layer transcoders were introduced just this year. And the idea behind cross-layer transcoders is that you can trace how features interact with each other across layers. Um, and so you basically do the same thing. You have your encoder that takes the input to the MLP and projects it to on an overcomplete basis to get your features. But your features map not just to the same layer they're in, but to all the subsequent layers. And this is what I mean by this. Basically, you have a decoder matrix um, per subsequent layer. And again, you have a loss, an MSE reconstruction loss, an L0 sparsity to make sure your features activations are sparse, and a dead feature penalty to just make sure that you don't have dead features and all your features are actually used. So we use this cross-layer transcoders to study multilinguality in LLMs. And our setup was the following. We studied 5 languages: English, French, German, Arabic, and Chinese. And our data basically came from FineWeb 2 and OpenWeb text. We collected the data and we trained 8 models actually, one on the Tiny Stories data set and one on this mix of FineWeb to OpenWeb text. And we had 4 training mixtures per model. A mixture where English is dominant with 90% and the rest is uniformly distributed across the four other languages. And we just do the same thing with the 70%, 50%, and 20%, where the 20% is the model where that was trained on the same amount of data of training data on across languages. We also made sure that our tokenizer was trained on the 20% data mixture so that we avoid any sort of bias in our study. And yeah, we trained the GPT-2 models and the Tiny Stories model using the Carpathy implementation. I'll just skip this, but I'm happy to talk about it or just refer to the the paper where it was introduced. But basically, we use this replacement model attribution graphs to study our 8 models. And the first question was, do LLMs really think in English? So we introduced this multilinguality score that was defined as the probability that a feature is like is English or French or yeah. And we defined this entropy score that just signifies that when it's low, the feature is language specific, and when it's high, it's multilingual. And we found that basically for our models, we have this pattern where models are language specific in early layers, they become multilingual in middle layers, and then they go back to language specific in the last layers. We also tried to study and to see if there is actually any alignment with English, because as we saw earlier, people have found that models in general translate to English, or they go through English before ending up with the right answer in the original language. And so we just measured the cosine similarity between um, each of the features and the final in-embedding vector of the English token and the native token. And we found no evidence of like higher alignment with English than the other languages. We also found that through like the training of our models, that there is like, even in the case where the model was trained with English dominantly, um, it still performs well with German, French, and Arabic, and it generalizes, even if the training data was basically containing only 2% in in the other languages. Yeah. And so we also, to answer this question of do LLMs really think in English, we studied a bunch of prompts as we see here, and we found that for determinants, like in this example of it was a piece of cake. By the way, this is a graph that shows you what are the features or the clusters that are used by the model to predict the next token, which was off here. It was a piece of. We find, just like previous studies, that the model does not really use any multilingual features to predict determinants, but it does when it comes to general words such as Friday or seasons here in this German example. So to summarize, we found that models have a multilingual space in middle layers where they think or where they process their prompts. We found that there is no such a thing as an alignment with English, at least in the models we studied. And we found that the clusters are actually also the clusters of features are multilingual, and they tend to be the same across languages and across mixtures, which shows that there is this there is this pivot language, but it's not as obvious as one can think, because it's not English, obviously, but it's somehow there. It's computationally there. And yeah, the things the other question we wanted to answer is actually why do models fail in non-English languages? And we studied this example of the opposite of men is across languages and across mixtures. And we found that basically the reason is a competition of circuits. So we have a reasoning circuit and a copying circuit that just copies from men in previous tokens. And once we intervene on the clusters by scaling up the right circuit, the reasoning circuit, and scaling down the copying one, we end up with the right answer. And we do this just by basic steering over the features in the clusters of interest. This steering schema is actually general across languages and across mixtures. And whenever the model fails to answer correctly, we found that scaling with the right amount on the right cluster ends up having the model answer correctly. We also find that this pattern of English being better performing than the other languages is due, at least in the examples we studied, is due to the fact that English triggers stronger activation in the task-specific circuits, men and women in our task, but also say sports cluster in the other category completion task that we studied, but I didn't present here. And we also found that in Arabic or in languages that don't really work well, the problem can sometimes be due to subtokenization, and that due to this, the model might end up using the first layers to just take those subtokens and make them up to like the actual word. And we also found that there is a weaker edge strength from the embeddings in those cases to the target clusters that, like the clusters like men and women or say sports that actually do the heavy lifting. We also found in the 20% case, and even if the models were trained on the same amount of data across languages, that there is a preference towards Latin script. And that this is basically due to the fact that there is a cross-lingual feature sharing between Latin languages than the other languages. Here, by other, I mean Arabic and Chinese. Last questions that we wanted to answer was, how do models handle language? And we found that basically we have a set of high frequency features that activate in late layers. And those features do like they are responsible on the most of the like the language part in the model. And we also found that when we intervene on those features by scaling them down or like zeroing out them and scaling up features from other languages, for example, here in this seasons example, we have a seasons graph in English, another one in French. If we scale up the seasons features from this graph in this French example, and we zero out the French features, we end up with the model answering in English rather than in French, even if the original prompt was in French. We also found that in general, the features with token activation were actually language features because they were activating on the corresponding language more than the other languages. And we found that English uses less English features or language features in late layers than the other languages, which was actually the same thing Anthropic found in their post, or like they talked about in their post. So for future work, we're intending to open source Lawrence library that maybe he will talk about if we have some time left, and open source the CLTs we have, but also train others on larger models, and analyze those larger models to make sure that our findings generalize. And finally, our question of why is English better would also benefit from this scaling because like it will allow us to study more sophisticated prompts and a larger number of them. And we can also, with those like larger models, we can study moral, cultural stuff, which will be interesting. Yeah. And also we're open to your suggestions to like think about what to do next. Thank you.
This is great. And thank you so much, Abir, for your presentation. So this chunk of purely your talk will go to YouTube. I think you presented greatly.